Alright, hell yeah, we got a new book for Christmas. So this is pretty sweet. In it, just a bunch of perplexing problems, as it says, and this is the first one. The first chapter is on geometry. What we're going to do today is the cube problem. And we're going to do it in its probably the simplest form. There's going to be a part 2 to this video where there's a classic one where if you have like a room where an ant is right there on this wall, and then, let's say a spider's right there, and then a fly is right there, like 1 foot down from that wall, 1 foot up. The question is, what is the shortest distance for the spider to get to the fly? Now, this one's just a little bit easier version of that problem. We're going to have an ant at point A, and we need to get to point B. And I think I'm going to share the mindset that I used. But I might actually, so like the first thing that and even if I didn't use this mindset, I should have. Like the first thing to do is just, state what appears might be a fairly fast way to get to point A to B. I would say I would go along this edge, get to this corner, and then go directly to point B. Okay, hell yeah. And then, so that'd be kind of the first solution. The second solution might be, and this second part kind of gave me an idea of what what would be the fastest route. I said, let's say you just decided to go for whatever reason, just pick a direction. Like, hey, let's go this way and then over to point B. Like maybe one of the question is, would it be possibly faster to go like down halfway and then straight over? And my brother helped me answer that question. Because if we take a look at that, if we go, straight to the middle of the block and then go straight over, well, the reason that wouldn't be the fastest, because all we would have to do is just cut that corner and just go straight to, this point right there. And so that would be kind of a visual proof of like, well, you're always going to be moving in straight lines. And I guess I'll have a clarification. If you're on a face and you're going to be traveling across that face, you're going to have to use a straight line. So then the only time that you would actually change your, if we're looking at it kind of like this, the only time that you would actually change your orientation would be at a junction here. And the answer to this, if you just, okay, so I'm going to state that a lot of these problems, whether they're riddles, perplexing problems, especially problems like this, because they're not in a textbook, they don't have problems prior to it, they don't have problems after it. This isn't a problem in a series where you do, an easy one and then you move up to it. You're just given this, and it's just like, shoot, you got to go for it. So that's, I'm more interested in doing problems like these. I think there was a time where, hell no, I didn't want to do anything like this, because you get to where you just get into dead ends and you don't know how to how to even grunt through it or make any headway. And I love geometry problems because they're usually kind of technical, but they always involve Pythagorean's theorem. So anytime you see a triangle or some sort of geometry, hell yeah, if you don't get into the habit of knowing that you need to pull out Pythagorean's theorem, always do. And and then you can even just say what you want to find. If I know this, so if I say I'm going to go from A to this corner and then directly down to B, kind of make it nice and crisp. All right, so if I'm going to take this route, well, I should get a length for it. So that's what we're going to do right now. And we're just going to say this box has sides are a length of 1. So I'm going to go from here to there, that's going to be 1, and then I got to go across here. Well, I know that these two sides of a right triangle are 1, and so we're going to use Pythagorean's theorem to find the hypotenuse. Hypotenuse would be C, so hell yeah, C is going to be A squared plus B squared square root that. Cool. Alright, so that's going to be 1 squared plus 1 squared square root of 1. So I guess I'll just write it in 1 squared plus 1 squared square root. That's going to be 1 squared is 1, so this is going to be 1 plus the square root of 2. Square root of 2, it's always good to also, especially when you're using, things, anytime you're using like e or pi or the square root of some number, just always know it's kind of decimal equivalent. I mean, even from a total guess perspective. I mean, e is 3, pi is 3, square root of 2 is 1.5. And then have like a second guess that's a little bit better. Square root of 2 is 1.4, cool. And then you can hone it in, 1.4142, you know what I mean, who cares? E, 2.7, cool. Do I know if it's 2.71? Not today. Hell yeah. Alright, so booyah. So just quick guess, this is going to be 2.5. You know what I mean? I'm just guessing that's 1.5. This is a very fast way to do mental math. And we're just on our way. But we know that's just a guess, so it's going to be it's going to be 2.4142. Hell yeah. Now, I think the easiest thing to do is just be like, well, just experiment. You know what I mean? And we don't have to go down this face and over here. So let's just go this way. And let's because this video is gonna be getting into derivatives. We're gonna kind of learn what a derivative is and how that's going to be useful. And I guess to state the obvious is that we're gonna get an equation. This is an equation for length, but we're gonna get an equation where we can kind of change a variable. And then once we get that length, and then maybe the variable's just x. So we're going to have an equation that's like blah, blah, blah x plus, maybe something x. Maybe it's x squared. Maybe it's the square root of x over here. It doesn't really matter. We input one parameter and we get a length. And then so what the derivative helps us with is, we want to change that. And then when we change it, maybe our length increases. Maybe when we change x, our length decreases. Cool. And what we want to know is we for sure want our length decreasing, but we want to know the point where, hey, we're going to change our x value so it decrease. It might just decrease a little bit less. That makes sense in the real world. And then it gets to the point where it doesn't decrease no more, and then, maybe the x increases. Okay, so whatever x value that was, that's going to be the parameter that makes our length the shortest. And the derivatives are set up where it's just like, hey, change in, your function. And I hate when they write it like this because it seems like you lose half the world's population. But for our problem, it's going to be, hey, change in length. But what are we going to change? Well, we're going to change this variable x by 1. This is kind of the standard form for a differentiation. We for sure want our length to change, and because we want to know like when it's decreasing, and but we're gonna know that by changing this variable by 1. Holy hell! Yeah, this is tripping me out too, because it's just like, well. I kind of almost lost myself. But in this form says the change in length. It must mean that I'm taking, like, hey, this is the length when maybe my variable x is 1. I don't have an x in here. But then I need a length when I choose a new number for x. X is 2. And we're just going to say x is an incremental, but oh man, I probably should put an x in here. But essentially, if this says change in length, it's like, well, it's going to be that length with x2 minus this length that we found. And so now let's just look at this. Because if I choose like a new, sorry I don't have a parameter in here that we're changing, but we will in a second, but you get it. We potentially know this is not going to be the shortest. We know this is going to be one of the longer ways to go. It's not the longest. I mean, you could just zigzag back and forth and then get to B. Obviously, that would be hella long. But this might, just from knowing how these problems are like riddles and stuff, I mean, that's one way to deduce it. Be like, oh yeah, the obvious answer is probably not going to be the answer. That's why I don't like riddles, because they trick you, potentially, in showing you, hey, look at that. It looks like A to B is just right there, so why would you go any other direction? Okay, but that said, we found this length, and we know that it might be a little bit high. So we're going to choose a different path, and that's going to be L2. So, and I'm sorry I don't have a variable x in here, but you get it. So we found that new length L2, and maybe that was a little bit smaller. Cool. And then so we have this there's the original L that we found. Maybe that was a little bit bigger. So when we take this minus this, we're going to get a negative number. So we're going to get some sort of negative number. And that means that the change in length got smaller. That's all that says. If I say, hey, my initial length is 2.4, and then that's my initial measurement, and then I'm going to measure again but go a different route, and then I'm going to get 2.3. Okay, hell yeah. Well, the difference between those, whatever I did to do that new route, L1 minus L2, that saved me 0.1, you know what I mean, units or whatever. Could be miles if this cube was, a mile long cube. All right, hell yeah. But then the derivative has this idea that you're going to divide it by, the amount that you changed. So I guess we need a variable because we want to kind of analyze what this derivative is telling us. All right, hell yeah. So let's throw in a variable. So I chose to go from A to this corner to B. One thing that I want to do is just move over here like 1 unit. So I think it's going to be easier. I'm going to make an executive decision and change this cube. It's going to have a length of 10. Because now I just want to move 1 unit over. I want to go from A to this point and then directly down to B. And see if that's shorter. Because if it is, hell yeah, then we're on the right track. Okay, so if back to this. If I change the length to 10, this is going to be 10. Because I went from A, 10 to that corner. And then the Pythagorean's theorem would be 10 squared plus 10 squared, square root that. So we're going to have 10 squared is 100, so we're going to have the square root of 200. Nothing really changes, and this is kind of fascinating too. Like how do you, so this is going to be 10 plus the square root of 200. Anytime that you get the square root, just know that you're always going to be thinking about taking that 200 and, hey, this is 100 times 2. Okay, hell yeah. I mean, sky's the limit. You can do as much as you want, but this square root of 200 is the same thing as the square root of 100 times 2. And this is a kind of a cool property about squaring things. Same thing, if I had 100 times 2 and I squared it, this is the same thing as 100 squared and then times 2 squared. Same thing with square root. It doesn't matter if this is a 2 or a 1/2, because that's what we have right here. So that kind of links. And so this is the same thing as the square root of 100 times the square root of 2. Okay, square root of 2 we're just going to leave as is, but square root of 100 we know that's 10. So this now becomes 10 plus 10 plus 10 square root 2. We know that square root 2 is 1.414 times 10 is 14.142. So I have 10 plus 14.142, that's going to be 24.142. And I just moved the decimal place over. So hell yeah. So our length is 24.142. Alright, hell yeah. So now we're going to, sorry this thing's so small, but we're going to go over a unit of 1 and then find the new length. But this is the pace that I like to do these problems, and the reason why is like, hey, I can at least do something, and by doing something I can gain a little piece of information. Sometimes like you're making a huge misconception and actually what you're doing is false or something. But even just by going through the process, you might stumble across some of that. I did that with an Irodov problem. I didn't realize it was complex, and I just made it simple. But it gave me the wrong. I was getting the wrong answer for hella sure. So all right. Anyway, so yeah, just this idea of just doing one thing and then kind of getting closer to maybe an understanding or an answer. So we're going to use Pythagorean's theorem. This is a right triangle. We have a side of 10, a side of 1. So I know what this hypotenuse is going to be. And then here, it's kind of same thing. Let's see. Is it the same thing? Well, my right triangle is going to be over here. So this is going to be 9. This is going to be 10. So now my hypotenuse for this. Okay, so now I'm just going to say this is L2. Forget the x for a second. I'm just going to say this is L1. Well, I guess we're going to call that L0 for the initial one. We're going to call this one L1. And yeah, that works. We have a 1, I don't know. But anyway, so we have, so what is this new length? Well, it's going to be that hypotenuse plus that hypotenuse. All right, hypotenuse A plus hypotenuse B, let's say. Okay, so this is going to be square root of 1 squared plus 10 squared. Hell yeah. And then we got to add this. This is going to be the square root of 9 squared plus 10 squared. I don't know, and I don't know if you agree, but it seems like Pythagorean's theorem is so basic. You kind of learn, that's the first thing you learn, and it's almost the first thing you might forget when doing a complex geometry problem. Not that this is super complex, but it's just, I don't know, it gets thrown under the rug. All right, hell yeah, so let's do this. And let's even do this. This is going to be the square root of 101 plus the square root. 90 squared is 81. This is going to be 100, so this is going to be 181. All right, and doesn't really help us because I really can't factor 101. I think it's a prime number. And 181, 8, 9, 10, I don't know, that could be non-factorable too. It's not a factor of 3, it's not a factor of 2. It could be a factor of other things though, like 7. 181 divided by 7. Nope. And 181 divided by what's the next prime number that's not a factor of 2 or 3 or would it be 11? Well, it's definitely not 11. 181 divided by 13. 181 divided by it's not 15, 17. 181 divided by 18, 19. Nope. 181 divided by 23. Is that a prime number? 181 divided by 27. 27 is not prime. Anyway, all right, hell yeah. So we're just going to pop this into our calculator. So we have the square root of 101 plus the square root of 181. And we get 23.5. And is that less than 24.1? Hell yeah. So we have a check on reality that taking this route was a winner. Now, this is the part of the problem where, you know, you might not get it right away, but it's just like, okay, if we did one thing, couldn't we just come over here from 2? Couldn't we just say, hey, we're going to be 2 from this edge and see if our length is less? And for sure. But then the other thing that I did with this problem is I saw, you know, about this point in the game, I saw, well, like, let's say, I mean, if I just thought I was going to go down this side and then go at a 45 to B, I realized, oh, isn't that the same of just going 45 first and then going down this side? And yes, that's obvious that that's the same thing as our length initial. Cool. And then so from that perspective, I could have just aimed for a spot that was just 1 unit over. And then so I'm going to go to this point, and then I'm going to go straight down. And had I done that, well, this triangle is going to be 9, 10. So we have the hypotenuse of a 9, 10 triangle. And then this triangle, the hypotenuse is going to be 1, 10. And so that's going to give me that number L1. So even just right there, this length is going to be longer. This length is going to be longer. If I move inward, I'm going to be shorter. And so this picture right here is probably a little bit, you know, gold, because you're just like, oh yeah, or for me, I'm just like, oh hell yeah. Like, I'm sure now, at some point, I'm going to reach a point where I'm going to get the shortest distance. But still, I was skeptical. I don't know a lot about, you know, higher up math and topography. And so I was like, well, I was going to leave myself open to be like, well, maybe at the quarter. Maybe at like 1/4, that's going to be, for whatever reason, that's going to be the shortest distance. And then right in the middle is a longer distance. You know what I mean? Just because. And you could create a scenario where that's true. Just make a curved, you know, you could, if this box is, you know, higher up, kind of bulged right here, then maybe actually heading towards the middle is going to be the longer path. And you could create a topography where going right at the quarter mark is going to give you the but anyway, so I was just open to that. But then I don't know if I can actually Yeah, let's take a look at this, because I think making a graph is like the thing that no one wants to do. But so now we have this scenario where I'm going to call this point 0, this point 10. So we have 0 to 10. That's going to be that edge. And if I'm at point 0, or if I'm at point 10, the length that we're going to churn out was going to be a maximum. And that length was going to be 24.1. So whether I go to this corner and then down to B, or a 45 to that corner and then straight down to B, I'm going to hit both of those points. Now if I said I was going to do 1, and I guess this is now 0.9, you know what I mean? If this is 0, 1, this is 9. So if I hit those points, then I'm going to be a little bit better, and I'm going to have 23.5. So I'm going to hit that point right there and that point right there. And so I'm going to get something that probably looks like this. So that's where I was just like, hell yeah, it's probably looking, you know, something like that. Or, you know, right in the middle, we're going to have like, that's going to be the best place. That's going to be the lowest length. So from that observation and seeing that I could duplicate it on that side and then also draw this graph, but I was still open. I thought, well, maybe this is one of those cool problems where it's just like this comes down here, hits a minimum right here at, like, you know, let's say the quarter, or wherever we thought, you know, down to a quarter, and then pops back up and then does some sort of like W shape. I thought that was going to be highly unlikely, but at least I was open. I identified this as a polynomial, and I was like, hell yeah, you know, I'm still open to that idea. But at this point in the game, I was just like, hell yeah, probably right in the middle is the fastest, you know, so hit there and then go down to B. If I'm going this side, I'm going to come down to this middle and then go to B. And then here is so now, since we know that, now we're going to go straight towards that middle. And that's going to be a distance of 5. After this, I'm going to grab a new sheet of paper, and then we'll go over the derivative and how to set up this variable. Because what we're doing is we're changing this distance. You know, like if I said it's going to be 1, then that's going to give us, you know, this length. If I said this point is going to be 0, that's going to give us this length. And if I say that point is 10, that's going to give us that length. So basically, this distance away from this corner, that's our variable x. So now, I mean, you could think of it as, hey, if I hit this middle, my x variable right there, x is 5. I'm going to have this triangle. It's going to be a 5, 10 triangle. And then I'm going to go down here, and that's also going to be a 5, 10 triangle. So I think, so when x is 5, and I think this is going to be the length minimum, it's going to be the square root of 5 squared plus 10 squared plus the square root of 5 squared plus 10 squared. But hell yeah, so now we're going to see if we can actually do this without a calculator. This is going to be 25, this is going to be 100, so we're going to have 125. Alright, so plus 125. But now we can do that thing where we can kind of factor. We know that 125 is the same thing as 5 times what? 5 times 5? Oh, no, did I do this even right? So we have 125, 5 times, oh, I didn't think, oh wow, yeah, so that's actually pretty sweet. Yeah, I did not realize that. But yeah, 125 is 5 times 5, because 100 is 5 times 4, and, no, what the hell? No, 125 is 5 times, what? 5 times, holy Toledo. So how many 5s are in 100? Well, yes, I need to start from the basic. This is why I'm bad at mental math. If I have 100 divided by 10, you know, there's 10 $10 bills in 100. So how many 5s are in 100? Well, there's going to be 20. Cool. And so how many 5s in 25? 5. So we have 25. So 5 times 25 is 125. Yeah, that's what I was thinking in my mind, but I just couldn't get there. Oof. And then, so that's going to be 5 times 5 times 5. Because, you know, 25 is 5 times 5. So we can change the square root 25 into square root 5 times 5 times 5, and we know that square root of 5 times square root of 5, both of these are going to be 5. Square root 5 times square root 5 is 5, and if you can't see that, that's the same thing as square root 25 times square root 5. Square root of 25, hell yeah, is 5. So we have 5 square root 5. So now we have 2 of those. So we have 5 square root 5 plus 5 square root 5. And if we had to add these, yeah, this is interesting. Anytime I see kind of something funky, I just say it's oranges. So I have 5 oranges, and I'm going to add 5 more oranges. Well, how many oranges am I going to have? I'm going to have 10 oranges. Hell yeah. So that's, but yeah, for whatever, I don't think this is just obvious. You know, we have 5, 5 square roots of 5 plus 5 square roots of 5. I don't think it's obvious just to get 10 square roots of 5. For whatever reason, I just don't think that is. But call them 5 oranges. It's just a qualifier. It's no different than having 5 20ths plus 5 20ths. Like, and even here, I could use the same orange analogy. Whatever your denominator is, it has to be the same for sure. But just call it, hey, we got 5 oranges. You know what I mean? Because you can factor it out. Let's say that's what we're calling an orange. Cool. So then you have 5 plus 5. You know what I mean? Or you could just say, hey, these are oranges. It's funky. So I have 5 oranges plus 5 oranges. Cool, I'm going to have 10 oranges. And just don't forget the oranges. Alright, hell yeah. Alright, booyah. So 10 square root 5. Now, I don't know what the square root of 5 is, but I do know the square root of 4 is 2. So I'm just going to guess this is like 2.2. 2.214? Sometimes I guess like that because then, I mean, I did this one the other day. I'm probably not getting any closer. I knew there was a 3 in there. I knew it wasn't 2.3. Well, I didn't know if it was 2.2 or 2.3. But it's 2.23. So, hell yeah. And there's a 6, so it could be 2.24. Alright, so sweet. So square root 5 is pretty close to 2.25. You know what I mean? Call it a day. Honestly. So, yeah, it's really difficult to start memorizing. Sometimes you can memorize, but then memorizing like 3 random digits is just that. It's just a memorization, where then your memorization could be off. You know what I mean? If you're just memorizing pi as 3.1415926, maybe from here, you know what I mean, it's just, I don't know, I could be off. Alright, so same thing here. It's just good to know pi is 3. I don't know, pi is 3.14. I don't think you're ever going to, no one is ever going to forget that pi is 3.14. But for sure, E, 2.7, that's as good as anyone should be able to do. You should never forget E is 2.7, but you're going to because you're never even going to consider E as a decimal. 2.7 what? I have no idea. We're going to actually throw it in our calculator. 2.7, oh yeah, I forgot that, yes, it's a 2.7 18281828. So, sweet. But 2.72. Alright, hell yeah. Okay, so, sweet. So it was going to be 10 times 2.25, basically. So it's going to be 22.5, which was going to be our lowest point. And the graph is going to look like that. And we're going to have 22.5, but actually it's going to be, let's see if I remember this. Is going to be square root 5 is square root 5, 2.236. There you go. And I don't mind, there's a lot of numbers that, hell, you remember to 3 decimal places, you're going to be way accurate. And square root 5 is one of those because it's 2.2360. So it's very accurate. It's almost like knowing it to another, well, within another half decimal. Because, anyway. Alright, so hell yeah. So we're going to have 22.36. So we got 22.36. That's going to be our minimum length to get to A to B if we have a cube of side 10. Now if we have a cube of just side 1, it's going to be 2.236 multiplied by whatever the length of the side is. So 2.236A might be the length minimum. Okay, so now we're going to use the rest of this video to go into differentiation. But before we do that, let's do this. 125 plus the square root of 125. And we get 22.36. Sweet. All right, hell yeah. Okay, so this is how, just playing around with something and then going back and being like, oh, well, yeah, I could have just set up an equation right away. So this was going to be my first attempt. And then my second attempt was just choosing some sort of length over here. We're going to call that variable x. And even that might be the hardest thing mentally, because I know it was for me, like calling anything a variable is just like, I don't know. There's something intangible about it where you kind of lose touch with reality. But here's a way to gain reality back. One, can your variable be 0? And then what's your max your variable can be? So I could easily see this could be 0, and then I'm just going to get the length from A to this corner to B. So cool, I have that check. And then what is the most x could be? Well, it could be all the way out here, and we're still going to call this a 10 by 10 box. I think that's very useful. So sweet, so x could be 10. And this is every equation. You get a polynomial. Every polynomial either goes to positive or negative infinity on both sides of the coin, because it's a continuous function. It either starts at positive or negative infinity and ends at positive or negative infinity. And it can be really useful to figure out, like, hey, how much money you're going to make, maybe an x squared. Maybe you're going to make exponential amounts of money, but just for a few days. You know what I mean? So cool. So your graph is only useful from day 0 to day 3 if someone's given you an x squared amount of money if you work 3 days. And maybe that's what you want. But hell, if you kept working for infinity days, you'd make infinity money. So there's always that aspect. Anytime you're working with a graph, there's always, or any problem in general, just always like, hey, when does this problem make no longer any sense? Now we have a geometric shape, so obviously we could scale it to the tiniest little square up to the biggest square. But, I mean, even from that perspective, you do have limits on distances from there to there to there to there. Like, there is some height. People wanted to know, like, hey, what's some basic physics problems? Well, just an understanding of, like, how big you can have things. I love, like, first chapter physics, because I do ones like, my favorite that I did was how many... Could you have, in dollar bills, could you have $1 trillion fill Earth's largest container ship? And the answer is no. It would overflow, but you wouldn't need two. You know what I mean? You would just need just a slightly larger container ship. But then if you had 1 trillion of those container ships, would they fit in the ocean? Or if they did fit in the ocean, how much ocean would they take over? Well, they would take over all the ocean and then be stacked up 60. You know what I mean? Not 1 million, but there'd be 60 container ships stacked on one top of another, and then filling every possible, place in the ocean. So those are just problems from, taking something and then scaling it up. I bring up a square because at a certain point, there's no square planet. And so at a certain point, you have a square that will have so much gravitational force that it'll just tear itself apart. And that's kind of a fascinating one. Like, like that almost gets me fascinated in this kind of a separate problem. But at what length of a 2x4, if you dropped, and this one, for whatever reason, like I think, like for whatever, it doesn't make sense to me because, and I don't know if I've never done this one or, and thought through it mentally, but just from a material mechanics perspective, wood can take like 6,000 psi. Well, some of the deepest waters in the ocean have a psi that's greater than 6,000. So, and wood, that's the strength of wood. And if any component in this wood reaches a, pressure of 16,000, like the grains, especially like if you're pulling on it, you know what I mean? And then across a face, you're applying tension of 6,000 psi, it's going to break. Even if it's in compression, you're going to get those molecules to slide past each other, and you're going to get breaks. And those are at a 45 is kind of fascinating. So there is a... but then if you just had a chunk of wood that was kind of square, you could probably drop it into the ocean and get a higher pressure, because it would just be the same thing as like the hydraulic press channel of just, you know, pressing this thing at all different sides, where, you know, it's not going to theoretically break. And the molecules are going to get compressed together. Once you release that pressure, it might fall apart. But I thought this was a scenario where if you had a long 2x4, the pressure on the outside is going to make it split in the middle. And I just by lowering it into the deepest part of the ocean, I just thought that was fascinating. Okay, hell yeah. So that was a total aside. But it was reasonable, because we're talking about variables, and it's confusing to even just have this x here. I don't like it, but then I can be okay with it, because I know it's like, well, for this problem, x from 0 to 10 is like, hey, that's legit. Because even when I don't think people like to graph stuff in their calculators. You know, let's do it. Let's do x squared. And then you graph it, cool. But that thing goes to positive infinity and positive infinity. So there is this useful part of your graph that you're using, something that's tangible to your problem. And I think that gets overlooked in a lot of mathematics. All right, hell yeah. So, so cool. So now that we have that, we're going to hit this point, and then we're going to go to B. And this meets all of our axioms. Like, we're not going to go to a point halfway and then jog this way, because we already proved that the shortest distance is a straight line. But then once you get to like a different face, well, then yeah, maybe you change your change your angle. Now, obviously, I don't want to give the answer away if you've never done this, because I didn't know the solution, you know, to the whole... I don't even want to say the general simple solution, but that simple solution, you don't learn anything. And so I forget things, because I've never come across this problem, maybe way back in like high school or something. So this was brand new to me, and I did not know this simple solution. But once you actually Google this problem, it's almost hard to actually see the problem without seeing the solution, because the solution is so simple, and once you see it, you can't unsee it. So keep that in mind if you want to, you know, try this for yourself. But it was cool doing it this way, because I was able to do that harder problem where we have the spider here and the fly there. And that required a partial derivative. It was the first time I've actually ever used partial derivatives in a realistic problem, like a physical problem where I'm like, oh, hell yeah, that's partial derivatives. And I actually had to look up how to use them. And so that was fascinating. So this video is kind of part one, where we're just figuring out what the hell a derivative is. Okay, hell yeah. So now here's what we do. So we have everything that we need to know. We have this variable x, but there's one more. In geometry, well, let's just start in, and that will pop out. So now I want to know the length of this line. So now our x, I mean, you have to think that x is a number between 0 to 10. I think that is very useful. Okay, enough said. So our length is going to be this hypotenuse. So it has a side of 10, and then a side of x. So we have 10 squared plus x squared. Okay, hell yeah. And then to get from there to B, now what is this? Well, our right triangle is over here. So we know this side is 10. Now what's this side right there? So this is like, besides writing the Pythagorean theorem for the first equation, anytime you do geometry, write this. The second equation, like for sure this comes up all the time, is I know this length, and it has some sort of junction here. I know this to be 5, and I know this length is 15. So then the question is, what is this length? So this setup occurs all the time in complex geometry problems. And so it's another thing that's going to get overlooked. No one's going to spoon feed you this, because to say that this is... So yeah, let's do this one first and then apply it to here. Because to even just to say what this is a problem in itself. And from a high school, or even, you know, I could say even, I'd be like junior year in college, and for whatever reason, that would be tricky to me. Like, what is this length? And cool. So for this problem, if I know this total length is 15, this is 5, well, just intuitively, this is 10. And then, so this is where, you know, I've started making videos where it's just like, hell yeah, do what you do with the numbers intuitively, and then go back and ask yourself, what did I do to the numbers to get 10? I mean, did I take 5 plus 15 to get 20? Nope, I guess not. I mean, did I take 5 plus 15 to get 20 and then divide by 2? No. You know what I mean? So how did I get this 10? Well, I you know, and I think the easiest way is I said 5 plus something. And anytime I do this, I just do like a box without. I think this is very useful. So 5 plus something is equal to 15. Because I think humans, we like to know addition before I would ever look at this and be like, oh yeah, this is just 15 minus 5. I do not see that. But I see that, hey, 5 and another number has to equal 15. That's why it's so intuitive. So 5 plus another number is 15. But if we look at this as an equation, we can get what that something is. Bring the 5 to the other side, that's 15 minus 5. So that's the answer to this one. So now we can go back, and this is where just even having one variable is just, it messes with you. Because you're just like, well, I know that this length is 10, so let's do this. So we have this length is 10. This length is x. Now what is this? See, even just right there, it's not intuitive. But you can just still say, it's like, well, what did we do with these numbers? Let's do that same process. So x plus some number is going to equal 10. Cool. So then this is an equation. Rearrange it for whatever that is. So this is the question mark, is equal 10 minus x. Hell yeah. So that whatever we did in this little equation is the same thing we're going to do right here. So then, because this, like, no one's going to spoon feed you this. You know what I mean? So, because in geometry problems, this happens all the time. You're going to be like, hell yeah, that's x, and this is 10 minus x. And you're going to write it that fast, and no one's going to be like, well, where the hell did that 10x come from? And it looks funky as, you know, 10 minus x, and then x. And so, and then let's even do this. Because I say this whole length, so this whole length, yeah, let's geometrically write it, is going to be x, and I'm saying this is 10 minus x, and this whole thing is 10. Now, does that jive? Because even I can't see it. You know what I mean? I visually cannot see that, but if I say, and this length is 10, so if I say this length is 10, which is equal to x plus 10 minus x. Cool. And I guess if we just have a plus, it's just x plus 10 minus x. And so x minus x is, so those x's go away, and we have 10 is equal to 10. All right, hell yeah. I think that was worthwhile, even for me to go through that whole process. Because just to see it one way, to be like, okay, this is x, and this whole length is 10, yeah, 10 minus x. But there's so many problems that, hey, you're going to know a part of something, but and it's going to be a variable, but that also means that you probably know this other length because you know this total length is 10. And then so you can put that same variable on that. It just has, just looks different. 10 minus x, and that's x. Okay, booyah. So now we can begin the process of, and that was necessary because now we know this length of this right triangle. So we said we got to A to that point, and that was going to be this 10 squared plus x squared. That was that hypotenuse. Now we need to go all the way to B. And the right triangle here is 10, and then here it is, 10 minus x. So we have the square root of 10 squared, and then let's put this in parentheses, plus 10 minus x squared. So this is now our length. And this is our length with a changing variable. it's no different than what we did here. We were just able to change our variable once, twice, and then intuit that, oh, just by kind of geometry and what we know about, you know, it's like there must be a low point and it's got to be halfway. That's how we got to this solution. But now we can do the same thing with this equation. And if you've never done this before, if you've, I guess if you know how to do differentiation fairly well, but you still don't know the practical aspect of it or like why it works, I think this thing is pretty good. Just having in your calculator and just writing this in. I have this, I can set x. Let's do x is equal to 1. So we're going to, 1 stored as x. Cool. And now let's just write this equation. Square root of 10 squared plus x squared. And then plus square root of 10 squared plus parentheses 10 minus x squared. Cool. And push enter. And we got 23.5? Hell yeah, that's going to be the 23.5. You know what I mean? We throw in 0 stored as x and bring that equation up again. We get that 24.142. Okay, so this is what I would do, is just play around with this. So we're going to go at store 2 stored as x and bring that equation up. We get 23. Cool. So this is the only number I remember. Well, when x was 1, we got 23.5. So 23 is less. Okay, so now we're changing x. And this process is pretty cool because we're changing x by 1. So I'm going to say 3 stored as x. So 3 is now x. Bring that equation up. We get 22.6. That's a lower number than 23. So we're getting a shorter distance because this equation is our distance, our total distance A to B that we need to travel to get there. Cool, so 4 stored as x. Bring that equation up, is a smaller number. Hell yeah, is 22.4. Now if you're on point, you can maybe see is like, hey, are we, is this number, like, is it, like, okay, let's go back. So we had, we went from 23. So when x was 1, we were at 23.5. When x was 2, we're at 23. When x was 3, we're at 22.6. But now when x is 4, we're only at 22.4. So yes, we're getting a shorter distance, but now it's like not as much. So let's go. X stored as 5, bring it up, and we get 22.36. Hey, is that smaller? Hell yeah, cool. So we're set there, and then we go 6 stored as x. Because like I said, have parameters. X could be 0 or it could be 10, and then that's it. X can't be 11. Okay, so when x is stored as 6, we're going to bring that equation up, and now we have 22.4. Is that less than 22.36? No. You know what I mean? And then so 7 stored as x. You know, go a couple more. Is this less? Because maybe we made a mistake. No, this is getting bigger again. So our last known point that x was the smallest was 5. 5 stored as x, and we got 22.36. And 4 stored as x, just to show you, was 22.43. And 6 stored as x was 22.43. So let's go back to 5 stored as x. And this is the process that I do. Like, there's no way I do stuff fast at all. I mean, my videos are slow, my thinking process is slow, but I'm always finding ways that I can grind. You know, anytime that I can actually, you know, like do something, I'm going to do it. You know, any time that I can be like, oh, there's something I can do, so let's do it. And even for this, I mean, this might shock you, probably not, but hell yeah, I made a little box. And what I did is I took this corner and then measured to the middle. And then I would just, because I wanted to, like, after I realized this scenario, I was really hoping for this W shape. I was just like, it'd be really sweet if for whatever reason this problem was cool and it had 2 places where like the middle was not the fastest way to go. So then I took this, but even this box, it wasn't big enough. I could hardly tell a difference between measuring from the center and then measuring a 0.5 centimeter away. You know what I mean? There was just hardly any difference. So then I measured 1 centimeter away, and still I was getting inaccurate measurements. So even for this box, it was too small. But, and the crazy thing is, I didn't even have to do a box. this was before I just used Pythagorean's theorem. But, and I want to be honest with you, is that when I saw this shape, I was just like, yeah, like the way I would solve it is I would make a box and then measure and then see if, you know, measuring from here to there and then going a 45. Well, hell yeah, that really did, I mean, I can just do that right now. This is a 4-inch box, and then so I'm going to be 5 and 5/8. Cool. If I go any other place, let's say the center, I'm going to go 4.5, and then I'm going to go obviously 4.5. So that would give me a distance of 9, and again, if I went this direction, I would be 4 and then 5 and 5/8. So this was 9 and 5/8, and if I went this direction, it's 4.5 and 4.5, so 9. So yeah, taking that like just very quickly, that was the fastest. But even from that, it was just so wild that I thought I needed to make a box, when now, like doing something like this, I could have just been like, well, yeah, Pythagorean's theorem was gold here, because I could have just said, well, hell yeah, I can just easily throw that into my calculator, figure out what this, if I went this direction, you know what I mean, the square root of 200 plus 10, and then go this, and then go to the halfway direction. Cool, the square root of 125 plus the square root of 125, and just compare those. So let's do that. So we have the square root of 200, that was this longer approach, and then we have the square root, or 2 square roots of 125. Whoa. No, this longer approach is 10 plus the square root of 200. The halfway is going to be 2 times 120, square root of 125. So hell yeah, so that would be a shorter way, and then at least I know that. And then let's say I, alright, no, this is good. But because this is the way to do differentiation without, you know what I mean? So let's do this process of like, well, what did we just do? I just said, I'm going to get the initial length of going down here. That's going to be 10, and this is going to be the square root of 200, Pythagorean's theorem. And then I said I'm going to go to this point halfway, and then hell yeah, I just thought that would be a good place to start. And then I got 22.36. But now here is how quickly you can see if this is the minimum point. I do this a lot in dynamics problems, or in a lot of problems just in general. If I just thought this was going to be the lowest point, I mean the shortest distance going through the middle, all I have to do is just bump it up just by a little bit. So if I said this triangle was 5 by 10, let's say this triangle is 4.99. Cool. So and let's, yeah, so that's what we're going to do, and then we're going to go back to this equation, and then we're going to also play around with it. But this is the first thing that I could have done is, you know, get this length. We have the square root of 10 squared plus 5 squared. That's going to be this hypotenuse. Plus the square root of 10 squared plus 5 squared. Cool, and that's going to be that hypotenuse. We have 5 right here and 10 right here. We have 5 right there and 10 right there. So that's that distance. We want to double check very quickly whether this is the shortest. So I'm going to boost this up to 4.9. Alright, change batteries. Okay, so I'm going to move this point up to 4.9. But if I do that, this triangle is going to be 4.9 and 10, but now my distance to B is no longer 5. It's going to be 5.1. And so that also, even just doing something like that right there, like really hones in on this equation. The fact that we have this variable is x, and this is 10 minus x. Because, and see, even for me, it's just like, I don't see the connection here. But let's say I say 4.9 is x, so I'm going to go to 4.9. What is this? That's going to be 10 minus 4.9. Oh yeah, 10 minus 4.9 is 5.1. So I'd have 4.9, 5.1, both those add up to 10. So this equation is, this equation jives. But I mean, I don't know, like I'll tell you all day that, yeah, even just looking at a simple equation, equations are difficult because it's hard for them to be visually significant in your mind. To be like, whoa, when I look at that, what I see is the fact that, You know what I mean? This whole thing is going to be 10, and when I change one, when I increase one, the other decreases by the same amount. You know what I mean? So cool. All right. That said, we can figure out. So back to, we chose the middle point. We have a total length of 22.36. Now we're just going to just move it just a tenth of a unit. So we have 4.9, and then for this triangle we have 5.1. So we're going to be moving along those hypotenuse. So we have the square root of 10 squared plus 4.9 squared plus the square root of 10 squared plus 5.1 squared. And hell yeah, when we do that, what happens is we get a longer distance. So that right there, if I said, well, yeah, it's going to be in the middle, I'm going to shoot for the middle. What's one way to check to make sure that the middle is the lowest point? Just move just a little bit off center, and it should be a greater distance. If it wasn't, if it was this W shape, and I just chose this W and it was a low point and not the lowest, then if I moved to one side or the other, it would be lower. So, yep. All right, hell yeah. Cool. Okay, so that shows that this middle section is going to be the lowest point, and I thought that was kind of an easy way to do it. So now let's go back to this equation that we were jamming on, and this is just the general equation for the length. And what's our x? Our x is 5. So we're going to do that same thing. I'm going to put now I'm going to do just 4.99. Well, let's just say I just did 4.5 as x. Throw it in there. And we get a bigger number. So now I'm going to go 4.9 stored as x. Do I still have a bigger number than this number? Yeah, it's still bigger. So 5 stored as x, I'm going to throw that in one more time, and then I'm going to go 4.99 stored as x. And then this 4.99, just a little bit off, is a bigger number. We got 36068, and this is 36067. Okay, sweet. So we found our shortest distance. The shortest distance goes right through the midpoint. Cool. So now for the rest of this video, what we want to do is, we know this is the equation for length. How do we take a derivative? And what do we do to that derivative? Like, why is that a useful thing to do to figure out what this minimum x is? Because right now we just figured out that x is 5. At x is 5, we have length minimum. We have the lowest, we have the shortest distance you need to travel to point B. All right, hell yeah. So bringing it home, yeah, we'll see how long we spend on this. Cool. So we know that's the best route, but now what we started out with was just this route. We thought that might be pretty good. It wasn't. And then what we did is we just kind of moved this way just a little bit. I'm calling that x. And we realized that it was a better route. Just even moving x is 1. When x was 1, that length was better than hitting this corner and going 45. Okay, so then we wanted to change x. X could be anything from 0, this corner, up to 10. So we kind of had that. And then we needed to figure out this length, because when we actually go to figure out what the length is in terms of x, so we have length in terms of x now, so that's another way to write this. This is going to be 10, cube of 10. So this hypotenuse is going to be 10 squared plus x squared. Cool, that's going to get us to there. And then how do we get to B? Again, this is our 90-degree angle. This is going to be 10, but what is this? This is going to be 10 minus x. Cool. So we have plus the square root of 10 squared plus 10 minus x squared. Okay, so this is our equation for any length at any given value of x. And we just know from, plugging into our calculator x is 5. But now we want to use this concept of derivative. And what we showed was when like 3 stored as x, when x was 3, it was 22.6. When 4 stored as x, it was 24. But 2 stored as x, I should have done that one first, was 23. So I went from 23, and then it dropped 0.4. So I had 23. Then I had 22.6, and then I had 22.4. So this is a change of 0.6. This is a change of 0.2. So, and in both of these, x was 2, x was 3, and then x was 4. So I changed my x value by 1. So that's what we did here. I changed my x by 1, and then I got a change in the length by 0.6. I changed my x value by 1, I got a change of 0.2. So this is what we're kind of comparing. And even at the beginning, when 0 stored as x, 0 stored as x, that was going to be that 20. So x is equal to 0, we get a length of 24.14. And then 1 stored as x, we get a length of 23.5. So by changing x by 1, my length changes by about 0.6. No, 1 point, sorry. Well, yeah, 24.14 minus 23.5. Yeah, it's 0.64. So I get a, yeah, let's do this all the way down. So we have, yep, we have this minus this term. And we get 0.64, good enough. So 2 stored as x, we're going to get 23. So this 23.5 minus is 23. So now our change in length is going to be 0.5. And 3 stored as x. And then 23 minus that answer. So we have, so when x is 3, we get 22.65, and our change is going to be 0.36. Cool. When x is 4, we're going to get 22.4, and our change is going to be, what's our change? 0.2, just 0.2. Cool. And then x is 5 stored as x. Our change, so when x is 5 and we get 22.36, our change is going to be 0.07. So our change is going down. So, and this is kind of cool because it's a scenario where we can change x by a whole value. You know what I mean? We change x by 1, and then we get a change in length of 0.64. Now some problems, hey, you change x by 1, this might be 640, and then this might be 500, and this might be 360, this might be 200, this might be 70, but it's still approaching and this is decreasing. So we're actually, what I should have done actually is taken 23.5, this new length, when x was 1, and then subtracted 24.14. And this shows you that we have a decrease in our length. So our original length, our original guess was 24.14. We change x, by 1, and I actually decrease my length. And I keep changing x by 1, my length keeps decreasing. But if I go to x is equal to 6 stored as x, and I get 22.43, so I should be taking this number and then subtracting x equals 5. And then this gives me a positive change of 0.07. And going this way, now my length is increasing. It's going to be symmetric. So I could say this is 22.65, and my change in length is going to be a positive 0.2. But this shows you there is a point where, like, my length doesn't change. I hit a minimum. All right. Hell yeah. So, yeah, I do like going over derivatives because now we're going to get into it. But before we do, I like this idea that we change x by a value of 1. And when we do that, we know what the change in length is going to be. You know, if we chose x as 0, we get that length. We chose x as 1, we get that length. Chose x as 2, we're going to get this length. Or we're going to get that much change in length. I mean, if we choose x as 2, we're going to get this length. And we can see that's going to, we're decreasing our length. So that's what we're going to see. Now, so we have this equation for L. The derivative says, hey, let's take the derivative of L as a function of x with respect to x. So that's kind of how you would say the derivative. Basically, you can say it's just like changing this length L by changing x. And so that's exactly what we have done. We have changed x. Let's say x is 1, so we get that length of 23.5, and then we're going to subtract 24.14. And then what did we do with our change in x? Well, we changed our x by a value of 1. Now, I don't know. Like I think derivatives should be taught like this way, more on this idea of averages. Instead of on this idea, then, you know, like hocus pocus, if you make this change in x really, really small, you're going to converge on a value. But I do like this idea of, you know what I mean, having your equation and then you just changing x by something. We didn't have to change it by a full value, but I do like problems where you're able to. Where it's just like, hell yeah, I can change x from 0 to 1, and that's going to change my length. So that's what we did. But you could also, you know, say, hey, x is going to be 0.1. You know what I mean? And then we change x by 0.1, then our length changes. So let's do that actually once. So we're going to go 0 stored as x. We're going to get that length of 24.14, and then we're going to do 0.1 stored as x. And then we're going to get a new length. It's going to be less. We're going to take that length and then subtract it by the original length. And now we get a change. So between those, so the original length where x was 0 was 24.14. And then we got a length where x was 0.1. And that's going to be 24.07. So we get a change in length of 0.07. So we get negative 0.07. That's going to be our change in length. Cool. So now if we averaged this, if we said, hey, that's going to be our change in length from 0 to 0.1, hey, maybe we're going to continue, our length's going to continue to change at the same rate. So then let's just guess based on that what our length would be when x is equal to 1. So this was when we changed x by 0.1, and so and I want to change x by 1. So 10 times as much. Well, shouldn't my change in length just be 0.7? And hey, that's a fair guess. Our actual change in length between 0 and 1 is 0.64. Hey, that's pretty close to negative 0.7. So yeah, we're kind of in there. But we do have a discrepancy, so we need to talk about that discrepancy. Because now let's go up to 23.5. So we're going to have to get 23.5, x was 1. So now we're going to say x is 0.9. Cool. So very close to 1. We should get an answer pretty close to 23.5. So let's do this. So 0.9 stored as x, and then we're going to get that value. So this is our length is going to be 23.56. Our length at x equals 1 was 23.5. I don't even think I have that in there. I got to get that in there. So x at 1 is 23.5. Now what's the difference here? I'm going to take this 23.56 No, I'm sorry. I mean, visually we should have this one right there. But so we have x is equal to 1 is equal to 23.5. So here we go. We're increasing x and increasing. So x is 0.9. We get a length of 23.56. We know that if we increase x, we're going to get a smaller length. So we get 23.5. We want to know the change in length. That's going to be this number, 23.5. Minus 23.56. And now what do we get? We get a change in length of 0.05, And I should have taken this to more decimal places. But no, this was 0.0770. So this one was 0.0576. Cool. That's going to be our change in length. But if we went from 0 to 1, our average, so that we got right here, our change in length was going to be negative 0.64. So now what gives? Because we said if it's going to be, sorry, I got to slow down. This was a change in x of 0.1. So we could use this value and say, well, I want to change x by a full value of 1, so it's just going to increase this by 10. So we would have negative 0.576. And so these are the numbers that we're comparing. Negative 0.576. This one, negative 0.7. So we basically have negative 0.57, negative 0.58, negative 0.7, and we're wondering why it's not this negative 0.64. And we're wondering that because this negative 0.64 seems to be the actual answer. It's like, hell yeah, that's exactly what the change in length happened from 0 to 1. So why, when we look at the change between 0 and 0.1, we're getting this value. If we average that, we'd get this value. And then if we took the change in length from 0.9 to 0.1, we're getting a different value. What we can do is we can take these two numbers, this negative 0.7, add it to this, and then divide by, whoops, I need to get this 1 times 10. So we're going to take that negative 0.7, and I'll just get the actual number, times 10. And then we're going to add it to this negative 0.576 and then divide by 2. Because that'll give us the average. And the average change in length, if we do that, is going to be negative 0.64. And so that's going to be that same number that we got right there. Oh, yeah, and then I got to throw in the towel because that's not 100% true. The whole idea is that if we make x kind of relatively small, then we're going to get these two numbers, but the midpoint should be basically this average. But that's not quite true because now let's go back to our graph, and what we see with this graph is that if we change x, we're going to decrease. We're going to, if this corner is pretty bad location. If we go in one, hell yeah, we really shorten our distance by quite a bit. So the slope of this line is steeper, or the graph looks like this. Try not to use words like slope because we want just kind of a visual representation. So let's redo that. I'm going to redo that graph because I think it's useful. All right, heck yeah. Yeah, so we have the square, and this is going to be our length, and then we have 0 to 10. And we're getting pretty used to it where if x is 0 right on that corner, we got a length of 24.14. If x is 1 or 9, and yeah, do we have this pretty much? Yeah, there we go. All right, hell yeah. And then we're going to get 23.5. And that pen's done. Cool. So we're going to be right there. And let's go up to here. All right. So we're going to get something that looks like this. So we just had this. What we were trying to find was the change between here and here. So now if we blow that little chunk up, we're going to have like here, and then the actual graph is going to be a curved line. So if this is 23.5 and this is 24.14, this is 0, and this is 1. If you take a straight line from here to here, this is what our yeah. So yeah, this makes sense. This represents our average change in length, because we can just see that we take 23.5 and then subtract. I'm just going to say this is 24.1, and so we're going to do 23.5 minus 24.1. Oh hell no. 24.1 minus 23.5 is 3, is 1, is 6. And that's going to be 0.6. So we're going to call that. So we're going to get negative 0.6. That's going to be the change in length. But this is considered the average change in length. If we take this negative 0.6, and what's the units on this? So this is going to be negative 0.6. And let's just say the cube's in inches. So we have negative 0.6 inches per change in x of 1 inch. So yeah, the units on differential equations, I would actually write out and then say what you're even doing. So this is representing this average line. We know that this line isn't matching up perfectly with the curved line, but the cool thing about this, so this is kind of fascinating. The cool thing about this straight line hits this point at 0 and it hits the point at 1. So it's perfectly accurate right there, and it's perfectly accurate right there. That's why when I tried to figure out the midpoint, so that's just going to be the midpoint of that. That's when we got something over here more accurately of like what did we get? We got negative 0.7 for our change in length right there, and right here we got negative 0.58. So then the halfway point between those two, let's see if I don't have to use calculator. So we got 0.7, 0.58. We're going to get 1.28 divided by 2. That's going to be 0.64. Hell yeah. Trying to not use calculator. These pens suck. Alright, so we have 0.64. So now the question is, why, if that's the average, why do I get 0.64 and I didn't get this actual average of 0.6? And my bad, I mean, this should be, let's try to do this. So 0 stored as x, and then 1 stored as x, and then subtract that. So the actual average should be negative 0.639. So, we got 0.64. Oh yeah, but we're not going to. So let's take a look at this, because these are very close, and they should be. These should be very, very close, because that's why we this gets into. Like, let's say I got this point right here and then this point and then drew a line. Well, hell yeah, this curve goes way lower. But this whole idea of a derivative is making this small as possible. But I still think it gets to be too much to handle when you say this gets smaller, like, you know, even smaller than 1,000th of a whatever you're using. If we're using inches and I take x to be a change of 0.001, like I think that's considered pretty small. Your accuracy is going to be 99.9% accurate for the problem. So call it a day. I don't like the idea of taking this thing to an infinitely small chunk. I think you lose half the world's population when talking about derivatives. Okay, hell yeah. So, but I do actually want to figure out that difference. So now we're going to, so I'm going to store this in my calculator as, I'm going to store that in my calculator as a. We're going to go back to x is 0. And then we're going to do 0.1. And we're going to take the difference between those numbers times 10. And then store that, I'm going to store it as d. And then we're going to do this 0.9. So 0.9 stored as x. And then 1 stored as x. And take the difference between those two numbers. Times 10, I'm going to store that as e. So now when I go alpha d plus alpha e divided by 2, then I get negative 0.638. And let's take a look at that. So, and then we're going to store that as alpha b. So we have alpha a, that's the one that we just found out a minute ago, and then we got this new one, alpha b. These two numbers aren't the same. So if we go back to our graph, the average that we just taking these average, making a straight line, we were getting negative 0.6386. So that's the number we're getting. When we actually get Alright, hell yeah. No, I kind of messed something up here, and I'm glad I did. Because those two numbers should be pretty darn close. The thing that I'm trying to point out the difference, I'm making a mistake. Because if I draw this again, we have a curved line, and then we have a straight line. Basically the slope of this line is we have a unit from x is equal to 0 to x equals 1. So the slope of this line is going to be the rise over the run. We have, so slope is rise over run. And we have a negative slope. And so the change is going to be that 0.64. So we have a negative 0.64 and divided by 1. So that's where we're getting that value of negative 0.64, or more accurately, negative 0.6386. Now, and I'm saying like, hey, this is synonymous with kind of the halfway point down this, what am I saying? Oh, maybe two different things. I mean, just by this picture, this slope right here is our slope of this number. So if I took that and took the tangent along the actual curve, I would hit right there. But that might actually hit at an earlier point. And I think just by the shape of this, it has to actually. So if I say this is halfway and this is 5, this slope would actually occur at some x is equal to a lower number. Alright, hell yeah, because the same picture, we could do the opposite, where we have a flatter slope that gets steeper, still goes through those points. This slope is going to be somewhere along here, and alright, hell yeah, I gotta throw in the towel on this, because what I'm saying isn't true either, and what I'm this is like the rate of change of the slope, and in relation to that slope right there. So I'm just going to bow out of that. Yep, this is me learning to learn, because one of the aspects that I don't like is when you take a derivative, you do all your power rules and stuff like that. But I think for me, I kind of lose touch of, after I take the derivative, so we take the derivative of this, cool, we do that, what does that actually give us? Because when I take the derivative, I do get an equation, something something x, something something x, and this is the derivative. Cool, and then let's throw in a value of x. We throw in a value of x of 0. What am I going to get? Well, I'm actually going to get this number, because this was the change between 0 and 0.1. I'm going to get a number like negative 0.7, because this was the change, even though the change was negative 0.07, but my change in x was 0.1. So all said and done, it's like you get a change of negative 0.7 per a change of x of 1, even at that point. So when I do get this equation for the derivative and I throw in x is equal to 0, I'm going to get negative 0.7 or something close to it. And then if I throw in x is equal to 1, like I'm not going to get this negative 0.64. That's what I'm just basically sharing. I'm going to get this negative 0.567. That's the number I'm going to get. And if I want to get more accurate, we can do that just to show you. So we have a check on reality. So this x is equal to 1. I'm going to take x is equal to 0.999 and then x is equal to 1 and take the difference between them. Now we have a change in x of 0.001, 1,000ths. We have a 1,000th change in x. So my change in length is going to be very, very, very small. But I'm multiplying also by a very, very small number, so we get a relative change in length. And if we do it right at this 1, we're going to get something very close to 0.576. So let's go through that process. So 0.99, and this is a process that I would do just to kind of get an idea of learning what the derivatives are. And I get why people say stay away from calculators, but I do not get it, because numerical analysis and just like this kind of like guess and check, throw in a value is so important. Because let's go back to just having an equation like this. If you just see this, it doesn't mean you fully understand it. It doesn't mean that you've explored any of these points. The second you zoom in and actually calculate a value and then calculate a value right next to it, and you get a decimal numbers, and then you can visually see the difference between those numbers, that's going to be way more valuable than, And some people, if you're not using your calculators, you don't even see this graph. All you see is this equation. And I don't know anyone who can look at an equation, and basically see, maybe you can see the Pythagoreans. Even from here, you could be like, well, I have something squared plus something squared. That must be Pythagoreans. And this must be a side, and this must be a side. And I am going to do a little tangent and say, hell yeah, Pythagorean's theorem, because, let's say you just want to know a side. Well, that's going to be, let's rearrange solve for b, and that's going to be c squared minus a squared, square root that. So sometimes when you get an equation and you see, something something squared minus something something squared, you can still relate this to Pythagorean's theorem, but more as, hey, this is an equation for one of the sides. And you took the hypotenuse of some sort and subtracted it by the other value. So sweet. So yeah, there is an idea of looking at an equation and kind of getting a rough idea of what it is. Okay, so now we're going to do this. So we have 0.999. Store that as x, and we're going to figure out the length. And back to even what the hell are we even doing? So we still have this as our x, and we're basically going to say it's very close to 1. But 0.999, I'm going to get the length there. I'm going to increase to 1, and then I'm going to get the new length. And we know that it's going to be a shorter length. Okay, so there's that. 1 stored as x. There's that, and then subtract those two answers. This is going to be my change. It's very, very, very small. So we have a very, very small change, but we have to divide that by this 1/1000ths. Okay, hell yeah. And now we get negative 0.5695. And like I said, we get very close to negative 0.57. And so when, and this is when we get our derivative, when we do the power rule and what we do with derivatives, we can go back and throw in x is equal to 1, and we should get this number fairly close. I mean, and this brings up, if you actually want to hone in on what the derivative of x equals 1 is, well, you probably wouldn't take the length at 0.999 and then 1. You would take the length at 0.9995 and then take the length that x is equal to 1.0005. You still have the same change in x of 0.0001, and let's confirm that. 1.0005 minus 0.9995. Yes, it's still a change in x of a thousandth, but now let's use these two because that's going to be a more accurate change in length at x is equal to 1. All right, let's do it. So we have 0.9995 stored as x. And then, and I'm going to store this. All right, hell yeah. I just wanted to go up and, because we got that first estimate for our change in length at x is equal to 1. For the derivative. I don't even know what the derivative is anymore, but I'm going to store that, I don't know, just as alpha I. Cool. So now we have x is equal to 0.9995, and then we're going to go 1.123, and we're going to take the difference between those, and then divide by 1/1000. And so, booyah, so we get negative 0.56, not same number, but it's 46, so stored as alpha j. So alpha I was pretty close, but alpha j is going to be a little bit more accurate because we took the length on either side of 1 equally and halfway between, and it gets back to this. Like I said, it's just like, well, if this straight line, you know, and we know we have a curved line. For sure we know we have a curved line. But we're just hoping that curve has a midpoint at the same, you know, at the same location. Like a value. Like halfway down the... I don't even want to look at that though, because that trips me out. Okay, hell yeah. So now we are going to start in on taking the derivative of this equation. Alright, hell yeah. So now we're going to do the derivative. And so I rewrote it, kind of set it up again. We have our distance x, and we have this 10 minus x. This is the thing that we can change. And so here's our equation, just a general equation for the length from a to b going along that path, choosing a value of x. And so the derivative, you write it like this. The derivative of this length with respect to x, I guess that's how you say it. And I think it's useful to be like, heck yeah, let's put that in parentheses, because we have the derivative of that full equation, and because you would maybe say this is derivative of the equation Lx with respect to x. So you could have derivative of Lx with respect to x. So that's what I have right here. And then just how you would say this is the derivative of this equation with respect to x. And then I for sure, because the whole idea of a derivative of taking a change in x of infinitesimally small is just, it's mind-numbing. Where you can just come over here and be like, well, this is basically synonymous with just changing this equation when we change x. And the change means, I guess this change means that we're going to take, and this equation is length, so this equation Lx is length, and what we're going to do is the change in length, so the change in length is going to be the length at, you know what I mean, L2 minus L1 is going to be the length that x is equal to, you know, some number bigger minus length of x is equal to some number smaller. Cool. So that's that aspect. And then we have the change in x. If we chose a value of x here and a value of x here, then we're going to divide it by that change in x, which is that value of x bigger minus the value of x smaller. And so that's why it was pretty useful to do this, having a change in x of 1. That's going to be the easiest because that part of the equation, this part of the equation for a derivative just becomes 1. And then you're basically just wanting to know what the change in length is between two given values. So if I throw in x is equal to 0, I get that longer length. Throw x is equal to 1. Hey, we get just a little bit less. And the change in that isn't going to, the change in length is going to be the difference between those. So we kind of figured that out. And that was that first one that we really wanted to hone in on, this negative 0.64. Cool. And then just keep in mind that when we do the actual derivative, and then we throw in the value of x is equal to 0, and then x is equal to 1, we're going to get not this 0.64, we're going to get that, well, if we're close to 0, we're going to get that 0.56, and then if we're close to 1, we're going to get, let's see, what did I do? Alpha I, alpha j. Oh no, when we're close to 1, we're going to get negative 0.56. Yeah, we're going to get that. If we're close to 0, our value is going to be negative 0.7. And then we got negative 0.57. So those are the values that we're shooting for. And it's just good to have values to double check your reality. Because when it comes to doing the derivatives, it's fairly straightforward. The intuition of what a derivative isn't, especially when you're doing angles, because the derivative of an angle with respect to, well, I don't know, some of those derivatives, they're not tangible. You don't get anything tangible out of them sometimes, and that's kind of a bummer when you don't get something just easily tangible. But this is tangible. We change x, we're going to change that length. Okay, hell yeah. So now enough said, we're going to do the derivative. And the derivatives, the cool thing about derivatives is you can't mess them up. There's no possible way to not just grind and get an answer that's 100% accurate. Now there's plenty of places to make 1,000 different errors along the way. But the idea of a derivative is I mean, it's Newtonian or classical mechanics at its finest. It's like if I'm changing this from there to there, it's a continuous path. I hit every little point. And so if that's related to a length this, and I'm changing it, the change in this length will be a continuous, kind of a continuous function. So derivatives are this idea of continuity. Now hopefully, I don't know, maybe that's not true, because the next one I'm going to do, it's a discontinuous function. That's for sure. So maybe that's not, where it has definitely abrupt changes in the function itself. So that's something I would have to explore. But the whole point of derivatives is that if you have this equation, which is every known length given a change, this x can be continuous between 0 and 10, we know every single length on here. And so if we want to know, and the derivative is just saying, hey, what's the change in the length given a particular value of x? Like, how much is the length going to change? Cool, so that might be a 3-sentence way of sharing why derivatives aren't complex. Like, you can always just grind it out just using the rules of derivatives. All right, let's do this. So I guess I would change this. Sometimes it's useful, instead of doing the square root, change it like this: 10 squared plus x squared, and then we're going to take that to the 1/2. And sometimes it's actually really useful to get this in decimal form. So this is going to be this to the 0.5 plus 10 squared plus 10 minus x to the 2 to the 0.5. Cool, so this is what we have, and we're going to take the derivative of this with respect to x. So the rules are, if we have two things added, let's say I just had plus 3. I'm taking the derivative of each of these. That's kind of the first thing. So if I take the derivative of this, cool, and then I'm going to do this, and then the derivative of 3. Derivative of a constant is 0. Because also, it's just like maybe this can be useful, because we're saying when we throw in a value of x, we get that length. So we have that, check. When we change that value of x, we get a new length. Because this 3 isn't multiplied by x, or divided by x, or anything like that, this number will be the same for both. So if I have 10 plus 3, and then I'm going to subtract 7 plus 3, this is the same thing as just subtracting 10 minus 7. So the 3 did not change, from one point to another. And so it's going to cancel out. Since the derivative is a difference, it's how much something changed. So that's one aspect. From the rules that you use for the power, like you could do this. You could say this is 3, or maybe you can't. Nope, I'm not going to go there. So hell yeah. So derivative of a constant is just 0. Okay, hell yeah. Alright, so let's do it. So the power rule says you bring down the power. That's the first thing. So you're going to have 0.5. And then you have to take everything that's on the inside of this square root. Just write it down. 10 squared plus x squared. And then you're going to drop the power by 1. So that's where this is kind of nice, because then I can say this is negative 0.5. Cool. And if you did it in fractional form, you would just say this is something to the half. The derivative is 1/2. That's something to the negative 1/2. Actually, that might be easier, but sometimes when you get into second derivatives, it might be a little bit harder to see this goes to negative 3/2. You know what I mean? Where if this is just negative 0.5, what's dropping it by 1? That gives you negative 1.5. Cool. And then, in your calculator, you can just write that. That's the same thing. 1/2 is the same thing as 3/2. So it's negative 3/2. Okay, hell yeah, let's continue. Oh, whoa. So now we have this idea that the power rule, you can bring down the power right at the inside, change this by, drop the power by a hopefully I'm not saying half there, but drop it by a full unit, so it goes to 0.5 to negative 0.5. And then we have to take the derivative of the inside. And, cool. And I would put a parentheses here, because if the derivative of the inside has an x, 10 squared plus x squared, well then that's going to be 1 plus 2x, you know what I mean? Just using the power rule as well. And I would want to put that right there, because I would have to take that and multiply it by there. Here we just have, so 10 squared is a constant, so that derivative of that is 0. And so we just have this 2x, so that's going to be 2x. And then we're done. So it's fairly straightforward. So we're going to do that second one. Bring down the half. Write everything on the inside. And then take the derivative of the inside. And we're going to do that same thing again. Derivative of a constant is 0. Do a parentheses, because, hey, it gets real in here. What's the derivative of this? Well, just treat it like a new thing. We're doing U substitution, but I swear, the second you call it U substitution... Alright, hell yeah, new battery. Okay, yeah, and what we're doing is, we're doing U substitution, but I swear, the second someone says U substitution, like, my mind just shut off. It's just like, oh, hell no. But, I mean, essentially, I think it's better to do this derivative stuff, just getting used to the process. I think that's better than understanding the fundamentals, because, I mean, I think you lose the fundamentals of what's going on. Like, all these processes are just, like, so far from reality of, like, what's happening with, just doing it from a numerical perspective. Just, inputting an x, and then changing it a little bit, and then figuring out that difference, and then plotting it as a point, and then just charting that graph. You know what I mean? So, the fact that these power rules work, I don't know. like I think more videos, I should probably search out some videos on like, hey, is there an explanation of why they work like all the time? Because they just do. They're very fascinating rules. But anyway, so so what did we do? We brought down the power. We wrote everything on the inside, and then dropped this power by 1. See, I messed up right there. And then, yeah, these derivatives, especially going to the second derivatives, there's just so many terms, there's so many places to mess up. But now we have to take the derivative of the inside. Derivative of the constant is 0. Derivative of this now. Okay, like it's starting over. Well, bring down the power, so we're going to have 2. Write everything on the inside, and then drop the power by 1. Sometimes it's useful to just to throw the 1 right there, even though you don't need it. And then again, now we did that, but you still need to take the derivative of the inside. So the derivative of a constant is 0. The derivative of negative x is 1. Negative 1. Cool. So now we're done with that. So holy Toledo. And then even I was going to point out that even when you do x squared. So let's take both these. So we have x squared, and then we negative x. Both of them, we took the derivatives of them, and we're still taking the change in x squared with respect to x. We're using the power rule. We're bringing down the 2, and then right. So we're bringing down the 2 and then reducing the power by 1. So we get this. We get 2x. This one, we just, what do we just say? We just do this by, memory, that negative x just goes to negative 1. So let's treat it like the chain rule. I think this is pretty useful. So now for this one, we're going to put this x in a parentheses. So now it's kind of set up like that U substitution, the same thing we've been doing. Bring down the power. So do that. Write everything on the inside. Change this by 1, bring it down by 1, so we got 1. And then take the derivative of the inside. Cool. So now the derivative of x is just 1. And so I think that is probably easier to remember. Yeah, I don't know. But even just that, I guess you would write, if you had x, y, and this is y is equal to x. What's the change? What's the derivative of this? Well, what does that even mean? So here's 1, here's 1. And so so the derivative of this function, y of x, with respect to x, is the same thing as derivative of x with respect to x. Oh, yeah. So, even just right there, well, booyah. We're changing x and divided by the change in x. That literally is representative of 1. But let's continue on like we didn't just see that. So we're still taking the derivative of x with respect to x. What does that mean? So that means that when we take the change, and again, this is synonymous with the change in this function x with the change in x. Cool. And so even just throwing in parentheses kind of helps us out. It feels like we can analyze this just a little bit easier. Okay, so we have to. So when x is 0, so we have y. So y is a function of x, and so we can say y when x is 0 is 0. Y when x is 1 is 1. So that's what we're going to analyze. We're going to figure out that change. So that change in y of x. So hell yes, that's the derivative. Derivative of y of x dx is the same thing as change in the function y of x with respect to x. And so you have to take the second minus the first. So we're going to have 1 minus 0. That's how the function changed. The function, when we threw in x was 1, was 1. The function when we threw in x is 0 is 0. So this is the change in the, let's say this is the length of something. Let's say we, if we start here, we didn't walk anywhere, and then when we get here, we walked, 1, And so what was the distance that we walked? Well, we walked 1 mile, let's say. Cool. And, I don't know. anyway. But the derivative is that change when we changed x. And what did we change x by? Well, we changed x by 1. So that's going to be 1 minus 0. So you're going to have both those be the same. But I'll get better at explaining, but I love going over something that's so simple that you're just hand wave that the derivative of x is 1. The derivative of a constant is 0. I mean, I think I just showed there that, hell yeah, the derivative of a constant is 0 because it shows up twice equally in both sides of the equations and is irrelevant. Okay, now let's do this one. What's the derivative of negative x? Well, one of the properties of taking derivatives is you can take all constants outside of the derivative. So if this was, so let's do it. So we have the derivative of negative x dx. Because if this was the derivative of negative 3x dx, well, using that property, I can just take the negative 3 outside the derivative. So now I just still have that same dx. We just said that was 1. So this is going to be negative 3 times 1. Back to the original, what we were trying to do. This is going to be negative 1 times 1. So take the negative outside. We got negative 1. Well, and then the other thing that's helpful in math is just like, so we have the derivative of negative x dx. We can write this as the derivative of negative 1 times x. That's the same thing. You know, put parentheses around everything. I think it's very useful to, anytime things are being multiplied, to put kind of parentheses, because it just really shows that they're being multiplied. And then that you can separate them and do whatever you want with them. All right, hell yeah. So now you can easily see that you can take that negative 1 outside of the derivative, and we have that. And we just showed that that's going to equal 1, so we got negative 1 times 1, times 1 is negative 1. All right, holy hell. So sweet. So we just figured out. So this is our derivative. This is the derivative of our length with respect to x. And you still write it like this. You know, nothing changes on this side. And so what is, so that's where, like, I think when you write a derivative like this, it makes more sense. When you say, hey, I'm going to change this equation and then divide it by the amount that I changed x. Oh, this is so cool, and it really shows where kind of I lack. But I just feel like I'm a little bit narcissistic, where it's just like if I feel like I'm lacking in an area, I'll use the word blame, but it's just like someone along the way didn't recognize that. They're not recognizing that students, like, you know, yeah, sure, we all know how to do the power rule, but then even the U substitution, like I said, you might lose your mind with that. But if that's all you know about differentiation, and that was me, hands up, it's just like, oh, damn it, I don't know anything. You know, because then 10 years goes by, and you come back to it, you're just, I don't even know what a differential equation even means. And then so because even right here, like, I get to the point, it's like, cool, we have this equation, but what like, the other thing, so what I'm going to do is the units. Kind of the units are the equation, and what are the units on here? Well, the units say that it's going to be the change in length. Cool, we get that. That's what we want to try to find. But it's the change in length per changing x. So it's the for how much we change in x. And but this is where it's wild, because how it's written, if I just have this and I'm just pop out a number. Let's say for our problem it's going to be 0.5. So our length, you know what I mean, is pretty close to 24, but we know it can get better. And at any given point, we might have a change. This equation might pop out a change in length of 0.5. Like, you throw in a value of x here, you might pop out a number 0.5. Now, what does that mean? That means that at that point, yeah, this is wild. This is why I don't like the idea of derivatives, of like emphasizing the fact that this is a very, very small change in x. Because then when you go back to the actual equation and then you throw in a value for x and you get a number like 0.5, this isn't representing a very, I guess the reverse is also true. So yes, the reverse is also true, that this is only useful if I multiply it by a very, very tiny change in x. So if I say that my length is going to change by 0.5 inches, if this is 10 inches, I know the, so if I have a, all right, hell yeah, I know where to go with this. So let's write this equation in. And we're going to have, and maybe I'll just write it in here. So we got 0.5, and then we have 10 squared plus x squared to the negative 0.5, 2x plus 0.5, 10 squared plus 10 minus x squared to the negative 0.5, whoops, 2, 10 minus x to the negative 1. Alright, so let's graph this, and we're going to be going our windows, 0 to 10, so we should be pretty decent. Alright, hell yeah. Oh, and well, honestly, we just kind of want to go from 0 to 5. Like, we know that, so yeah, let's do this. So we're going to go window, we're just going to box it in. And we're going to go to 5, just so, that's the other thing. You get a graph, but you're like, I don't even know, I don't know what's happening anymore. But again, we're going to say, hey, x can be 0 or x can be 5, and we know that 5 is that sweet spot. It's the best place it can be. But now we're going to go for these values. So we're going to throw in a value. So when we throw in x is 0 into this equation, we get negative 0.707. So let's analyze this. This says, the units on this, and the other thing, if this is derivative, the derivative of the length with respect to x, again, write it like change in length, change in x, because that is going to be, this is going to be the units on here. This is going to be a change in length of negative 0.707. That's going to be the change in length per a change in length, or change in x of 1. Because whatever value you get in a derivative, just put a divisor, put 1 underneath it, and that is going to be the change in x. So this is going to be the change in the function per a change in x, or whatever your variable is. It could be a degree. It could be a degree in radians, which would be 60 degrees. That's why also derivatives with polar coordinates are a little trickier. Alright, hell yeah. So if we're at this point of where x is equal to 0, and we get like 24 is our length, and we know we can move x 5 places in and get a less length, and our length's going to decrease by this. So let's try that. So I'm going to have a change in x of 5, because I know I can change x up to 5 units or 5 inches, and this is going to be my change in length. So sweet, the change in x's kind of cancel, the number 5 stays, and we have 5 times negative 0.707, and that's going to be the change in length. But if I do that, so if we have negative, I guess that's sine 45, so if we have this number, and I multiply by 5, that's going to change my length by 3.54. So my length was going to be the square root of 200, which was, plus 10. So my length right here at x is equal to 0 is going to be 24.14. If I subtract this 3.53, whoops, 24, and then subtract or add this, so then my length is going to decrease. So this equation right here, just analyzed at this point 0, says that my length at the halfway point is going to be 20.6. Which, if we throw in 5 stored as x, and we go back to our equation for to get from A to B, we know that the minimum length is actually only 22.36. We already solved for that a long time ago. Okay, but from this value right here, it says, well, it says I'm going to be when I throw in a 0 into this equation, it's like, oh, hell yeah, you're going to reduce your x quite a bit. But that's only going to be for an instantaneous second. So that does kind of go back to the idea that this is going to be the derivative for, like, hey, a very small change in x, an infinitesimal change in x. Like, this value is only good. So let's bring that value up again. For maybe a change in x of like 0.1. So if we do that, if we say this times 0.1, and that's what we're going to use, and then we have 10 plus the square root of 200, and then we're going to add that. So now this should be the value at x is equal to 0.1. Because I just used this to go from 0 to 0.1, because I changed my x by 0.1, which is on here going from x to 0.1. And that's going to give me the change in length. And the change in length I found was, this number times 0.1. And then so I did it. I reduced my length by that much. But if I just go 0.1, stored as x, and then we actually put it into the actual equation, these numbers should be slightly different. Because this is what actually happens at 0.1. We get a reduced length. I should say we only get a reduced length of 24.072. But if I use this and then extrapolated it for a tenth of an x, a change in 0.1, it says I'm going to get way more change in length. But that's the whole point of, back to this graph, is that, and the graph we should be looking at probably is this one, just the actual length. So we're going to go 10 squared plus x squared. Plus the square root of 10 squared plus 10 minus x squared. So yeah, we're just going to look at this graph, and it's going to have and that's the other thing. Anytime you type an equation into your calculator, like what's the usefulness of this? It's going to pop out length, and so that kind of goes back to this graph. We're going to get something that has a length of 24 right there, and as x goes from 0 to 10, we're going to go back up to 24. So our window on that graph is going to be, I'll just do -1 to 11. So I'm going to go from -1 to 11, and then I'm going to go -1 in the y all the way up to 25. So -1 to 25. And then we can just instantly capture that. It's going to do the derivative first. But hell yeah. So this is the equation for the length being reduced. So if we see a value of 0 up on here, we see just the fact that this line is steeper than it is right here. Right here it has 0 slope. I tried to stay away from the use of the word slope, just because, I don't know, it's just more visual, just to get like a visual understanding of staying away from those words. But heck yeah, the graph is steeper right there. And so that means if we move x, so right here we moved x from 0 to 0.45, we actually travel down, we reduce our length, a little bit like more, but as we go from x, all the way from x to, whatever, to 0.1, whoops, we got to trace this. There we go. We're decreasing by a less. Oh, that was a horrible way to say that, but anyway, all right, so I guess I'll just say that is why the equation of a derivative is still kind of like a tricky thing to use, because it's only useful usually for like a short little window. It's going to change. But we can. So let's go back to get rid of this equation, and then just whoops, and then we'll graph that. So we're going to go -1, maybe -2, x is 6, and then 2. All right, so we're going to graph this derivative and just kind of analyze it. So we have a value of 1. So yeah, so we were talking about, oh yeah, and what we wanted, we had to check on reality when we when we took, like which one did we take? Yeah, we wanted to take the derivative when x was 1. And we were going to get that negative 0.5694. All right, hell yeah. So this was that paper. So, and yeah, and that's stored as y right now. So alpha y is that number. And we had alpha I and alpha j. And we thought these were pretty close. We thought alpha a was fairly close. That was taking 0.999, x at 0.999, or the length when x was 0.999. And then the length when x was 1. And then we took the change in length and we divided it by 1,000 because x changed by 1,000. And that's the number we got right there. But then we chose to take 0.9995 and 1.005. And that's the same thing. I mean, if you're gonna estimate something between x is 0.9 and x is equal to 1, you might as well do x is equal to 0.95 and x is equal to 1.05. Your change in x is still going to be 0.1, but you're going to hone in on that x, the actual derivative at x is equal to 1. And so the equation gives the actual equation is negative 0.56946, and this starting at 0.999 and going to 1 only gets 0.5695. So it's not as accurate. Where we come down here, we get 0.56946. And then it changes. So so that's going to be, so that was kind of our check on reality, that our derivative was and then I would do that if you can, because you're going to make so many little mistakes you know, using the power rules of derivatives. I do it all the time. Miss some negative signs. Forget the second part. Like, you know, bring down the power, change this power, but then forget to take the derivative of the inside. Alright, hell yeah. But we're probably overlooking the most important part of this graph. So this is the equation for the derivative. It says where the change in length, you know, for any value of x, our length is going to change. But there's one point on here, we have a 0 point. And that point means that at that value of x, our length ain't changing. So just one side of that value and just the other side of that value, or you could say, our length doesn't change. And back to, yeah, so this equation for our length, you know, we have this saddle right down here. And we get this value for 0. But just be cautious, because this equation might be like this. That this point, we might strike out where this point right here is like the worst place to go. And that was actually a maximum. It's still going to, if you talk about slope, that's going to be a 0 slope. Right at that point, we're not going to have any change in length for changing x. We could change x that way and this way, and look, our length doesn't change. But like right here, hell yeah, you move x1, our length now increases. But for our problem, it actually, so we change x by 1, hell yeah, our length decreases. And we get down here to our minimum. And so if we're at x is equal to 5, you know, we could change to x equal to 4, to x equal to 6. Well, our length hardly changes at all. So that is indication that we have a minimum for our problem. It could also be an indication that you have a maximum. So it's either or. Okay, but that's where this point crosses the x-axis, and it's x is equal to 5. So that says that at x is equal to 5, this derivative is going to give us a value of 0, and that is indicative of either a minimum or a maximum, but in our case that is the minimum. That's the minimum length when x is equal to 5. Alright, hell yeah. So thanks for joining me on this one. You know what I mean? This is probably the first video of kind of trying to explain derivatives. So maybe not my best. You know what I mean? This was my first rodeo. So thanks for joining me. And that's about it. You know what I mean? So just that last little bit probably should have been, I should probably talk about that way more. But I'm about done. So yeah, thanks for joining me. And guess what? That's a video.